It's a little bit time always to get back to work after stopping it. So welcome again. My name is Luca Massaron. I'm a GD, a Google developer expert. So I'm quite passionate, as you can understand, about Google technology. And maybe you already heard about me because I also write some books for beginners, a few books in the Dummy series and the Pact. From a Pact editor, and also maybe you have heard of me because of Kaggle competition if I'm passionate about doing data science competition on Kaggle. Tonight I won't talk to you about Kaggle, but about a different topic, about tabular analysis with TensorFlow. So after this presentation, I will just tell you that our agenda will just develop on 6 points. First, I will tell you briefly about the challenges that you can face if you had to analyze tabular data, and I will specify what exactly tabular data is with deep neural network, DNN. Then I will explore with you how a data pipeline could work for this kind of analysis, and especially remark the importance of cross-validation. This may sound trifle, but actually I've seen many times that the usual approach when you deal with neural networks is just to train on a subset and to test on another one. But when you are back to tabular data, so you are not in the field of images or text, actually you have to go back to the old paradigm of data science. So you have to cross-validate, absolutely. And then, this is very interesting, if you want to by yourself to apply the same techniques with your data, I will explain to you how to wrap everything in a data pipeline created with pandas and Scikit-Learn into a TensorFlow estimator or your Keras model. I will present to you very briefly a working example that you can try by yourself at home. And finally, I will just close with some motivations for all this presentation and all the work that has been done on this topic. So I guess most of you are quite accustomed with data science, AI, deep learning. May I ask you, how many of you have experience with, for example, using Scikit-Learn? Okay, so quite a good number. And what about TensorFlow? That's fantastic. So you are in the right place, and most important, I am in the right place. So I think we can just skip very quickly about this introduction. So as you know, just deep neural networks are a subset of machine learning, which is a part of a wider field of artificial intelligence. And of course, you should really have an idea of how a deep neural network works. So basically, just to recap, is a series of layers, and these layers are part of a cyclic graph. So you have your data flowing through a graph of nodes, computational nodes, which transform your data into the prediction you expect. So we can just skip also this. But we won't skip this slide. Why is relevant now to talk about deep learning and deep learning applied to tabular data? It is relevant because actually it's a new paradigm that we will apply more and more in the future. So we are accustomed to solving problems by developing software solution, by programming. Programmatically, we can make our software do what we want, but this requires that we embed some kind of intelligence and understanding of a problem into the software we write. Using deep neural networks and, for example, using machine learning, you actually have a different approach to problems. You set a set of examples, exactly what you want your software to do, and the software will learn by itself. And it can be breakthrough in many, many fields. In fact, we have already seen a lot of very interesting, great advances in many fields thanks to this technology. If today we are talking about self-driving cars, and it's not a matter that we won't see self-driving cars in this year, in the 20s. Maybe it will take another decade before we have something really functionally working on our roads. the important part is that actually this technology, self-driving car, is possible, especially because of deep learning. And we have deep learning in healthcare, which is quite revolutionary because actually now neural networks have been proved to be as enough good at detecting certain diseases as a specialized doctor. So they really can assist doctors in their diagnosis. And we also have deep learning in, for example, search engines. Maybe you have heard that Google is now powered by a neural network called BERT. Actually, Google has been using deep neural networks since a long time, but BERT is very special in its essence because it allows the search engine to be more semantically aware of the queries you make. So the queries you make will have best results possible now, thanks to this technology. And you, of course, voice search and voice assistant and automatic machine learning translator, something that you, I guess, have already used. And you also have sophisticated recommender engines and a lot of image manipulation generation. Later, Paolo will tell us about the GANs, the generative adversarial networks, which is a very crucial technology for all the image manipulation that you can hear nowadays on the news, such as, for example, the deep fakes, the technology that allows you to manipulate a video just placing the face of whoever you want on a pre-made video. But still, you don't hear so much about deep learning in a setting that we all know, tabular data, the data that actually you work with every day because it's the data that is stored in your company's databases. This data has a structure, data structure that dates back to the 60s, the relational model database. And you can imagine, because you use it, inside it you can find any kind of data, from text to images, but also most commonly just strings and numbers. And this is the most common value that you can find, a lot of nulls values. So you have challenges if you want to make this work, if you want to try to apply deep neural networks to tabular data. And these are exactly the challenges that you face. You have mixed features, so a lot of different kinds of data. You have sparse data, which is something that we overlook, but actually when you analyze with a deep neural network a language, so text, or an image, you have dense data. All your vectors or your matrix is full of numbers. If you take a database, you won't have so many numbers. And this is a problem for what actually makes deep neural networks work, backpropagation. Backpropagation doesn't work so efficiently if there are a lot of zeros in your values. It cannot propagate correctly the information. And moreover, you don't have any state-of-the-art architecture. If you want to analyze images, you have a host of different pre-trained models, and you can do transfer learning quite easily nowadays. You cannot do anything like that with tabular data. You, of course, has much less data, even if the databases are actually quite large, because specific problems often don't have all the data available that you want. There is a strong suspect from non-technical people about neural networks because they believe them to be black boxes, something that cannot be understood and explicate after you train that. And of course, if you ask any data scientist to do something with tabular data, they can much easily and in a faster way produce something using gradient boosting, a different technology based on trees. So why all the hassle? Well, let's take the words of Andrew Ng. If we really want to advance this field, we really have to take also this challenge, because it's the most common data that you can find. Tabular data is everywhere. And if we can find a solution also for small data sets, we can actually advance the field and have an alternative to old algorithms in data science that actually now dominate the scenario. But if you want to do that, follow me. You have to take some effort, first of all, and you have to take advantage of what is existing today. So you don't need to reinvent the wheel. You have to take advantage of Scikit-Learn, of pandas, which are the common ways to analyze tabular data and power them using TensorFlow and Keras. You have, of course, to take the effort to deal specifically with each kind of data you had to face, and you had to create by yourself your suitable architecture, but it's really not so difficult. And if possible, don't forget the best practices, that is to actually leverage any previous knowledge of the data that you have, the so-called feature engineering, which can be still very effective, even if deep neural networks are a kind of representational algorithm. That is, it can represent by itself the features that it needs to work. And finally, you have to test and tune everything using cross-validation, as I mentioned before. So using the right tools, and there is a good reason for doing so, especially for TensorFlow, because it's production ready and it has already all the necessary classes through its high-level API, Keras, that you need to work with tabular data, together with, of course, our power horse of data science, Scikit-Learn and pandas. And let's dive now directly into the data and into what actually you had to face in order to achieve a working model with neural networks and tabular data. Numeric data is the first challenge that you have to face, but it's easier because they are really numbers, right? You're just pulling your data, your database, they are all numbers, so it's perfect. You just feed them into the neural network. But actually, there are some tricks. If you're working with tabular data, you have a lot of nonsense variables which have been created for purposes different from learning. So you have low variance variables, you have a lot of missing values, you have a lot of strange distributions which are quite far from being Gaussian. So what you have to do? First of all, you have to filter all the data which is not useful for your work. You have to deal with the missing values, and dealing with the missing values means that you have to do some kind of imputation. You have to place a number inside the fields that are actually nulls or missing, but on the same time, you also have to mark what fields and at what position your variables you are missing data, because sometimes inside missingness there is information. This is especially true for tabular data. And you have to transform your data into being more Gaussian, because in this way your neural network will learn in a much easier way the information that it is inside the data itself. You have also to catch outliers. Outliers are quite common in this kind of data. They are kind of anomalous extreme values that can influence heavily the learning of your neural network. You have to catch them. You have to catch them when you are doing the data preparation or inside your neural network itself, using, for example, batch normalization layers, which calculate the mean and standard deviation of the batches that you feed your neural network with, and can, of course, intercept these kind of problems. And finally, don't forget, you have to normalize all your data. All your data should be in a very restricted range, or it won't work so easily, unless you put a batch normalization exactly after the input, which is not exactly what a batch normalization relation is made for. Okay, so I give you all the recipes, and you may be wondering, oh, it's a lot of stuff, how can we do that? No problem, actually. Scikit-Learn can provide to you all the functions you need. For example, you have to select the variables with at least a minimum variance. You have a function called variance threshold. And this function works very easily. You just pass a vector or a matrix of numeric data. You fit it, of course, in your train instance. This class will learn exactly the variance of that feature, of that matrix per feature, and it will automatically select exactly what you need for learning. And you can repeat that on the validation and all the test data automatically. The same for missing data. You have simple imputer which just takes each feature singularly, finds out the missing values, replace with a strategy you propose. For example, you can have a constant. You can say, okay, I just want everything to be replaced by 0. 0 is a neutral value and actually won't happen anything in your neurons. Just the bias will be working if you just pass this value. And so you just, of course, ask this function also to prepare a binary indicator, which is automatically prepared for your missing values. So you just pass a value which is neutral, and you just ask to be the network itself to estimate the correct value for missingness. Or you can decide for a different strategy. You can use a median, you can use a mean, you can use the most common value that can be seen on your vectors. And this is done automatically. One simple command with its parameters. The same for transforming your variables. If your variables are skewed, they are more difficult to be learned by your neural network. Let's make more Gaussian, more normal. So we have a power transformation. We come from statistical analysis, and based on the Bulge rule, which is applied automatically, they just can rebalance your data. This is very easy with power transformation function. Or you can use the quantile transformer, which is even more powerful because it binds all your data, it projects it into a distribution you are comfortable with. It could be the uniform or better the Gaussian distribution. And finally, if you want to just standardize everything, you just use a standard scalar. So you have a series of classes with their methods, and if you just put them all together into a pipeline, we will transform your numeric data and we will be ready. So this is much easier than thinking everything from scratch. And later we should view how this can be done even in a more easier way. But stay with me, because now we take more challenging data, which are the dates. Don't think that dates are everywhere in tabular data. And basically, how can you do? You just treat them in their time elements. So you split the data, which is dates, into year, month, day of a week, day of a month, day over here. A lot of information we can provide the neural network the sense of a flowing of time. Of course, all this data will be in numeric form, and sometimes it cannot convey exactly the fact that certain time measurements are circular. For example, the days of a week, actually between day 1, day 7, there is not 6 days of difference. It's just 1 day of difference because they are contiguous. So you just make them transformed by trigonometry using sine, cosine transformation. And finally, you may have, of course, to mark special dates, especially if you are working in a particular field that has holidays, recurrencies, important dates. This is done quite easily with pandas this time. Pandas, with a simple transformation, can convert your dates, no matter what their format is, into something from which you can extract everything you need. And you can also transform them in a very easy way using sine cosine transformation. So it's quite easy actually to deal also with dates. So even more difficult. Now we are at the latest step, which is the categorical data. So you may ask me, okay, Luca, we can deal with numeric data, which is the easier stuff you can find at tabular data. You can deal with dates, but what about categorical data? We have a lot of fields which are just strings, and some, of course, are quite easy to be dealt with. They are, for example, the gender, male or female, or actually no one declared their gender. So it's not that big deal. But we have some certain variables which contains a huge host of very different values, thousand in number. How can we do? Let's take each problem separately. First of all, let's talk about all the variables which have low cardinality. It means they have a low number of levels. Actually, low can be relative. It can be from a few ones, for example, like the gender, up to 255. Basically, it's a matter of your own judgment because actually you have to deal with them by a simple transformation called one-hot encoding. So you take each level singularly taken from the variable and you make it a binary variable. So if you start with a variable with 3 levels, it will become 3 variables. This is okay, even if you have a large number of levels, like 255, but it works, of course, just for one variable. And pay attention, by doing so, you take sparsity inside your input, because a lot of information will be 0. These kind of variables, as in the example you can see, can take the one value only when there is correspondence between the column and the represented level and the level inside the variable. So you take sparsity inside it. But it can work quite well. It's a very fast and actually a no-brainer solution. And the same can be applied if you have ordinal. Ordinal variables, it means you have an order. For example, you have a value, a score from 1 to 5, from good to bad. And in this case, you can just simply split the variables into its numeric component, which is ordinal, but actually not correctly ordered in the steps. So you have 1, 2, 3, 4, 5, for example, but you don't have a correct representation of a distance of 1 toward 2 and 2 toward 3 and so on, which will be taken, of course, by the one-hot encoding. The one-hot encoding will intercept this kind of effect. And this is quite good, but you still have to deal with a high cardinality. And the high cardinality are most challenging. How can you do? Well, start with the same approach you are doing with ordinal variables. So you just stick a number to them. So you have 2,000 levels. You just relate all the levels into numbers, arbitrary numbers, because you don't have any order, probably. For example, we are talking about company names or names of people, surnames, names of cities, names of products, for example. We don't have a precise order, but just convert them to numbers, and then you feed them into a special layer called the embedding layer. What does this embedding layer operate on the data? An embedding layer basically is a matrix multiplication. There is on top a transformation. This transformation is exactly the one-hot encoding transformation I told you before, but this is just temporary. So you create a temporary sparsity. Then you have a matrix multiplication, and by this matrix multiplication, we have a linear combination which will reduce the information you are providing by a larger number, for example, of columns, due to the larger number of levels, into a few dense features variables, which are inside your neural network. I will show to you a very brief example. So let's imagine to have IDs. IDs are very terrible. They don't have any meaning, but you have to analyze them because they actually represent a product, a customer, something very important for your neural network to learn. So you just provide a text, and the text, before being fed into the neural network, is transformed into numbers. Let's imagine we have this ID 8080. This ID can be transformed into a label, numeric one, which is in our case, number 3. Actually, you count all the possible labels that you have in this variable, and you have 2,400. So it's the third of 2,400. If you one-hot encode, you will have a 2,400 vector of zeros, but in position 3, actually in position 2 in Python coding, you have a 1 representing exact that value. At this point, the neural network, and this is done actually by the embedding layer by itself, you don't need to explicit it, will just make a matrix multiplication with a matrix of dimension 2,400, which is actually your input size, by, in this case, 4. But it can be 5, 8, whatever number you want. Even it could be a square matrix, 2,400. Because it's a transformation. You transform the sparse information by linear combination into dense vectors of exactly the dimensionality dictated by the second dimension of a multiplication matrix. In this way, you have your data perfectly fit for all the following layers inside your deep neural network. What you have to do, you just have to find the right second dimension of this multiplication matrix. That is just to decide which is the embedding, technically, dimension that it could be more useful for your data. Basically, if you have done data science analysis with principal component analysis, think it's a very similar technique. Also, principal component analysis is a matrix multiplication, a linear combination, which actually has very strict constraints because it will produce as results vectors called components which have specific characteristics. That is, in order, we will have to explain the most of the residual variance of your original data. In this case, there is not such constraint. The only constraint is given by backpropagation, because when initially this matrix, multiplication matrix, is set in a random fashion, it will provide some results which will be promptly correct by backpropagation, and you will have the correct weight set by your network itself. There are very interesting applications that we can find in literature of this technique. For example, at Pinterest, we use it for labeling in a special way all the pins that you can find on the different boards. So images and other objects in the different boards can be transformed into values. And actually, the most interesting part of this work is that once we did this transformation for one problem, they can reuse that transformation. So they take the multiplication matrix and they put it into another, for example, neural network or into a traditional machine learning algorithm. And it works perfectly for their purposes. And the same is done, for example, by Instacart. They are not using pins, they are using the baskets, the buying baskets of their customers, but they are basically using the same approach. So before going into a part where I will explain to you how to apply automatically all the techniques that I just mentioned to you, let me spend a word about cross-validation. I know you are already expert of that, but maybe it's not a bad idea just to recall why it's so important. So cross-validation, what does it mean? You have to prove the generability of your machine learning algorithm. How can you do? You make a test. So you try your machine learning algorithm on data that it has never seen as training data. And basically, you can do that with a test set, but a test set has some weaknesses. Unless you are gathering from a large number of examples, a large test set, you don't have the confidence that your test set has been drawn correctly from your reference population. So, for example, you can just work and test your algorithm on a biased test set without knowing it. For this reason, and also for the reason that most often test sets have to be at least of a certain dimension to explicate all the variability in your training data, it has been created cross-validation. In cross-validation, you divide your trained data into a certain number of parts, and iteratively, you just pick a few parts from training and one part from testing. So, for example, if you split your data into 5 parts, you will use iteratively 4 parts for training and 1 part for test. Each time the test will be a different part. So in the end, you will have a stochastic sampling of your population as represented by the training set, and you can take an average of your results and a standard deviation, which will tell you exactly how your machine learning solution is generable. And Scikit-Learn is the best for doing that because it offers to you a lot of different cross-validation strategies. Not just the simplest one, the one that illustrated to you based on the most simple sampling, but it can also be used for stratified sampling, for group sampling. For example, you have non-identically independent distributed examples in your data. Let's, for example, figure out you have the same rows from the same company many times in your tabular data. Okay, maybe you see no problem, but sometimes there are actually problems in dealing with this kind of information, because if you split the same data of the same company, partly in the training set and partly in the test set, you likely may occur in a inflection of your expected loss or your expected accuracy results, because they may be autocorrelated. One observation from the same company may be correlated with the second one, and so on. So this kind of strategy just puts, based on a group identifier that you provide, all the groups or in test or in training. So the same company may appear only in training or only in test. And finally, if you are working with time series, you have a time series split, which is a special splitting cross-validation for time series. Okay, so that's fantastic. We have everything, but up to now, we just talk about Scikit-Learn. How can we make it work with TensorFlow? And of course, with Keras. Well, there's a simple strategy, and you can find the GitHub address, an example of what I'm going to propose to you. In my experience, you have first of all to deal with your data in pandas format and to fit them into a cycle of cross-validation. It really depends on your problem. It can be just the plain cross-validation illustrated to you. Inside, after splitting into training and validation, so no transformation applied to your data, you have to use a class for tabular transformation. So that is a class that replicates exactly the strategies that you can find in Scikit-Learn, a fit transform or fit predict approach, which will learn from training data and apply exactly the same transformation in the test one. After you define this tabular transformation class and you learn from your training data, you just put everything inside a data generator. This data generator needs to be having certain specific characteristics, and we will present to you that in a few slides how it should be made. It will contain the tabular transformer, so it will generate automatically for, in this case, you can have a Keras model, exactly the transform batches with the correct pipeline splitting between the different kinds of data. And if you are using, for example, TF estimator predictors, or you are using a TensorFlow model, you actually can wrap the data generator using TensorFlow 3.0, and in particular the TF data, dataset function, everything inside an automatic function that will cache, split, and cache the data for you. So you can even think of a generator on the fly, picking up the data directly from your tabular repository, so your database. How this can be done? First of all, the tabular processor, nothing too esoteric. You just have to import the base estimator and transformer mixing classes from Scikit-Learn, so it will be perfectly aligned with Scikit-Learn specification, and create a fit transform methods able to process all your data, taking into account that for numeric, ordinal, low categorical, and categorical high cardinality data, you have to process accordingly to the precise specification that I provided to you. Of course, every problem is different, so you can find, for example, for some problems, you don't need, for example, to strive to have normal data. For some others, actually, it's very important. But basically, that kind of pipeline should be applied distinctly for each kind of data. Then, after you specify the tabular processor, you create your data generator. And most important, you have to present it with iter, next, and call methods, because they are the methods that actually are required by the TF data functions. and they can also help, of course, your generator to work better. And for Keras and for, of course, further wrapping by TF data, you have to prepare a get item and data generation methods. What do? Basically, they split and shuffle the data since the beginning, and you can access to your data by indexes. So by each index, it will just pick up exactly the data you need, and at that point, it will apply the tabular transformer that you have embedded into this data generator. And finally, if you need to use the TF data, simply you, after instantiating the tabular transformer, fitting of your data, so having it learn your training data, you can just instantiate the data generator and then put everything inside the TF data dataset from generator function, which will allow you to extend this kind of data to any model in the TensorFlow world that you would like to train. A few words before closing about the neural architecture. I will just give you a few hints that I learned from experience, because every case is completely different from the other. So in my experience, you start small, you try first small networks, and then you try to build more complex ones. Why? Because the approach is completely different from what you do when you analyze, for example, data like images and language. In that case, your strategy is different. You have hosts of data, so you start with very over-parameterized networks, and you try to regularize them, for example, using dropout and batch norm. In this case, you cannot do that. The approach is different. You start small, and you try to build up a more complex network, and you just keep control if it works or not by cross-validation. Then you try adding, after the first experiments, which actually can use just the linear activation, using nonlinearity. You have a wide range of choices. You start with the ReLU. You can try the leaky ReLU, which is very interesting because it will just propagate also the negative numbers inside your network. And then you can try more sophisticated and more specific for tabular data activation, like the ELU, the SELU, or the GELU. What do we do with? Basically, they tend to keep the propagated values inside certain value constraints. So actually, you can build very deep models with your tabular data. And then, of course, given the fact that they're using more sophisticated activation, you can try to stack more and more layers, so having more and more representation power. You, of course, have to filter, and this is a good suggestion, inputs using batch normalization, and I suggest to use dropout for controlling overfitting. Or if you are just using a very shallow model, also don't forget to use the L2 regularization, which can be set for dense layers. And finally, of course, you always try to embed the logic that you know into a parametric function. So you make your trials, but keep it open. And my suggestion is to wrap everything into a function. I will show to you because I prepared an example. We cannot delve too deep into this example because the time is, of course, running. But I will tell you it's based on a current competition, a quite historical one. It is the Amazon dataset. It is a dataset provided by Amazon a few years ago. It really past 5 years since actually we proposed the competition. And the task was to figure out if a person in an organization, specifically Amazon in this case, had the rights or not to access certain resources. So you can imagine is the triumph of categorical and especially high cardinality categorical data, because you have a lot of information about the roles inside the company, and Amazon is quite huge, and about the task and about the resources. So it was a very big trouble at the time because a lot of people just used, of course, logistic regression, and they had to create a lot of one-hot encoding. It was really terrible. But now the technology is different. So in this example I propose to you, first of all, there's a benchmark, and it's gradient boosting. In particular, it uses CatBoost, which is the best in class for analyzing categorical data, because it automatically embeds by a special system. It has incorporated into its algorithm anything categorical that provide to it. And at the moment is the best reference that you can have for this kind of problems. And then I apply exactly the same techniques that I illustrated to you in this presentation. And you can find here the code, and I will show to you just very briefly. You can access it, of course, also on Kaggle, so you can run it immediately and see it works. But if you go also on the GitHub, you have the collab link, so you just run it, and a collab will open for you, and you can run the example. Let's have a very fast peek at how the deep neural network, works. So as I said, embed your logic. So you want to use, for example, 2 layers. You want to use dropout. You want to use batch normalization. Make everything a function that by parameterization can help you, for example, augment the dense layers, change the embedding layers dimension, put a different dropout value, and so on, because you will have to test a lot. And especially if you prepare in this way your neural network, you actually can try even to tune it by using the same techniques that you use for Scikit-Learn algorithms, that is, for example, random search or grid search. I recommend to you random search, or even better, Bayesian optimization, but this is a larger topic that we won't touch tonight. So if you have a look with me about the beginning of this function, you will see that you have inputs, basically called numerical inputs, and it's all your numerical matrix, just entry by an input, and is normalized by batch normalization, and you have a dropout. The dropout is just at that point for making some feature selection. So maybe you have, of course, redundancy, you have collinear variables. Making a dropout will help your neural network to learn better. But that's all. After that, this data will just proceed to the dense layers. Then you have to deal with categorical data. And categorical data is done on the second block. So you have inputs, and each input is separated. Every categorical variable is provided as a single vector inside the neural network. This vector containing the labeled features, so they are ready in the numeric form. And each one is processed separately with its input. You see input with shape 1, and it transforms for the categorical embedding. You can just embed, of course, different matrix dimension for transformation, but I suggest a very simple rule of thumb. Just take the log of the number of categories you have, and you just add 1, and that actually should work quite well. Another strategy could be to take the root of a number of variables, and of course, if you have time, try more. Try, of course, very large transformation matrices and very small. It really depends on the problem. And then all these embeddings will be just concatenated together. So you imagine you have a huge matrix, numeric one, entering the network. This is just processed, and it goes to a concatenate layer. And then you have each categorical feature processed singularly into an embedded layer. Each one then proceeds to the concatenation. After the concatenation, it's just up to you. In this case, I did something very easy. So you have 2 dense layers just with a dropout after each one. And then you have, of course, your output node, which is a sigmoid because you are predicting a probability. And the results, I guess you are very eager to know that. Okay, if on this problem we use the CatBoost, we can achieve a ROC-RC around the curve of 0.876 using a deep neural network model with similar strategies. You can achieve a 0.863, which is actually worse than the CatBoost, but not really so far. The very interesting part, anyway, all with me, is that if you blend these results together, that is, you average them together, nothing more complex, you can get a 0.882. So it means that even if you cannot reach with a deep neural network the same performances of a cut boost, of a gradient boosting solution, if you do so, you will intercept your problem, most likely, kind of features, kind of information that gradient boosting cannot catch. And the proof is that if you blend this with a cut boost or with a light GBM solution, it will always perform better, I assure to you. So there are a few pro tips, but I think we can just close. At this point, I don't provide to you more technical information. The slides are available to anyone, and of course you can contact with me. Just have a look. There are more sophisticated tips for your neural networks learning tabular data. So we just conclude and wrap up. So deep neural networks are at the moment, given the state of technology, an alternative solution for gradient boosting and any other algorithm, classical one, or machine learning that you may think of for your data. They require some efforts. They require a Docker architecture. There's nothing already prepared. There's a new neural network prepared by Google Research called TabNet, but still to be proved how it works, if it is effective. Anyway, it's very interesting because it's based on attention, which is actually the hot topic at the moment. In any case, what's important is that you craft very well your pipeline, and using the technology provided to you by TensorFlow and Keras, you can easily access to the data and analyze it. And very important takeaway, entity embeddings are very important for this strategy because not only they are pre-made in TensorFlow and Keras, but also because they offer to you a solution that is exportable to any other solution you may think of, neural or not. And of course, most of the time, remember, even if your neural network cannot reach the heights of results of a gradient boosting, it probably will catch some information your gradient boosting will never catch, because remember, gradient boosting is analogy-based. Neural networks are interpolation-based. It's a completely different learning strategy. So if you blend them together, you will have the best result in class that can power up your projects. And with this, I thank you. And I don't know if we have a question time, but maybe later when we take some drinks together, you can ask me.
We can get one question. By the way, I'll show you where to get the slides. So there is a repository where you find all the slides there. So I'll show you there. I think we can at least like time for one question, surely, or one or two. Anyone? Otherwise, we are here also later for the break.
About the blending, the ensemble modeling part. Do you have any suggestion about like the weighting of the prediction of the gradient boosting and the neural network?
Basically, unless you have a out-of-folder strategy, so you did your cross-validation and you store your cross-validation results, you can try any kind of weights, but it's kind of snooping on the test set. So I advise against it. If you have an out-of-fold strategy, of course, you can use the out-of-fold and try to figure out the correct weightings. But in my experience, you just blend. You just take the average. So you just make 50% gradient boosting, 50% neural network, and it works. Of course, different weights can bring different results, but I always propose to be very cautious about that. You can just maybe make something working on your test set, which is not ideal.
Main idea of the cross-validation is just to find the hyperparameters like number of layer and not just all the weights, just the hyperparameters. Then, however, we have to train. Suppose we found the number of layers, the numerosity of every layer, and then, however, we have to train this with let's say 80% of the equation.
Okay, if I got right your question, yes, I confirm to you that cross-validation is very important because you have a wide range of choices when building this solution for deep neural network and tabular data. So you have many layers, many different kinds of activations, you can do many different kinds of transformation in your data. So you have many levers, and some levers may be tricky. They make, for example, work very well your solution for a specific sample of your data. But you want the solution to work on all your data you have, and the data you will receive in the future, which you expect to be of the same generative process, the same, of course, universe, the same sample, let's say so, of your training data, but it could also not. So cross-validation is very important for having a solution that works. After you did cross-validation, you figure out architecture, for example, batch sizes, number of rounds, average one. Of course, you have, for example, 5 or 10 different faults you test, and everyone will behave in a different way because working with different samples, you can train on all your data using that specific parameters, the information you got. You can expect the same powerful generalization that cross-validation provides to you. If I answer to your question?
Also learning rate, also the table.
Of course, everything. You have a wide range of parameters. Umberto, if you think we can just leave more questions later.
The speaker, so thank you very much.
Thank you for your attention.
I think then Paolo can talk about tf.function and TensorFlow. Then I see they're organizing the food, so also good. What kind of? Devi mettere quello per il. Vuoi usarlo? Non ti serve questo. È classico.
Okay. Grazie.
Okay, hello everyone. So in this talk, I'm going to tell you how to properly design functions that can be correctly graph converted using one of the new features of TensorFlow 2 that is called autograph, and its decorator that is tf.function. But first, a brief introduction about myself. So this is me. I'm a computer engineer. I lead a computer vision and machine learning team at a spin-off of an international company called Zurotech in Italy, in Modena, actually. And of course, I'm a machine learning Google developer expert. I have a blog in which I write mainly about TensorFlow and when I have time, about computer vision stuff, because I'm specialized in computer vision. I do a lot of open source stuff, and you can find all my projects on GitHub. I tweet sometimes, and I'm also an author of a book about TensorFlow 2, but I will talk to you in the last part of the talk about this. So we can start, and we can start talking about TensorFlow 2 and data flow graph. So in TensorFlow 1, there was a way of programming that was different with respect to what the usual standard programmer is used to do. So, I mean, usually programmers are used to program using an imperative way. So you just write your statement, you execute your statement, and you move on. In TensorFlow 1, instead, you cannot use this kind of programming, but you have to describe your computation. Because in TensorFlow 1, you first have to describe the computation, describing exactly using a graph to describe the computation. For instance, you can describe the input and the relationship between the input and all the other nodes in the graph. And then you have to create a session. And a session is nothing that the allocation of memory on usually a GPU, but you can do in basically whatever hardware. You should just allocate the memory. You just keep the computation. You put it inside your hardware device. So now you have created a session. And then you have to run the code. So you keep the output node. You can decide which is the output node. And you just give the correct input, and you execute it, and you get the output. But of course, programming in this way was too difficult. So with TensorFlow 2, they decided, the TensorFlow developers decided to completely change the way of programming, switching from the descriptive way to an imperative way. So right now, in TensorFlow 2, the default is the eager execution. Eager execution is exactly like using NumPy. Therefore, we are just using Python, and we are just executing statement step by step, exactly like using NumPy. But of course, data flow graphs, so describing the computation using graph, has too many advantages. For instance, graphs are fast because you describe once, you create this object, and then you can execute computation without using the Python interpreter. Graphs are also a language agnostic representation. I can create a graph using Python, then I can just generate this language agnostic representation that is a protobuf. And then I can load this protobuf using another language. For instance, I do this often in C++. Graphs are also easy to replicate and to distribute because, of course, you can just keep the computation and place it wherever you want and execute the computation. And another big advantage is that if you describe the computation using graphs, automatic differentiation comes almost for free. So for this reason, we have to keep these advantages also when using TensorFlow 2. And for this reason, the TensorFlow developers introduced tf.function and autograph. So tf.function is just a simple decorator. You can just decorate any Python function with @tf.function to auto-magically convert this function from Python code to a graph. Of course, this is a decorator, and this is the signature. And as you can see, autograph, that is another module, is used by tf.function. Autograph is more or less a compiler. It parses all the content of the function body, and then it's able to convert the Python control flow statement to TensorFlow graph operation. For instance, an if statement becomes a tf.con, while in Python becomes a tf while, and so on. So we can just try to have a look at what happens when we decorate a function using tf.function, and then we execute it. As you can see, we start in a different context where eager execution is actually disabled. So right now, when we decorate a function with tf.function, for the context of execution of this function, we are just back using TensorFlow 1. So no more eager execution. Now we have two branches. The first one is what happens on the first call. The first call is really important because autograph and tf.function works using the Python interpreter. Therefore, we have a single step that is the execution and tracing. So first, on the first call, you are executing step by step using Python every single operation, Python or TensorFlow operation, but step by step using the Python interpreter. But at the same time, we have also this compiler that is autograph that is analyzing all the abstract syntax tree of the function and is trying to analyze if there is an if there is a for, if there is anything that can be converted from Python to pure TensorFlow. Then we can merge these informations, creating a graph. So by the execution and tracing So we have to understand dynamically what Python is doing, and from the analysis of the syntax tree of the function, we can create a graph. After that, a unique key is created using the name of the function and the parameters, and then the graph is placed inside a map, so it's a local cache. So we have map, where the key is just a combination of the name and the parameters type, and there is the relationship between this key and the graph. Then, on the second call of any other call that is not the first one, we just try to create this ID. So we start from the name and the parameters. We look inside the cache, and if we find the graph, we just keep the already built graph. We don't do anything else, and we execute the computation. Of course, we have to take in mind that TensorFlow, from the first version, always followed a paradigm that uses static graph. So once we create a graph, it's fixed. It's a constant graph. We cannot modify and change the graph anymore. So we can try to have a look to what happens when we try to solve this problem using TensorFlow 1, TensorFlow 2 in eager mode, and then try to apply the function to our small eager execution function. So the problem is we have two constant matrices and a scalar variable, and we just want to compute the matrix product and add the variable. Really simple. So this is the TensorFlow 1 solution. First, we have to declare a graph. Of course, this is just for visualization, because in TensorFlow 1 there is always a default graph. But in this case, just to make it clear, I just created a graph explicitly. Then inside this graph, we have to declare the constants. So A and X, the constant variables, B, the variable. And then we just declare a node that is the matrix multiplication between A and X, and another node that is the sum of the result of the matrix multiplication and B. Then we have to write some boilerplate code that the one of you that use TensorFlow 1 are really used to have seen it, because you have to just create a special operation. This is the init operation, and where you just say to TensorFlow to initialize all the variables of the graph. And after that, you have to create the session. And in this moment, we placed the graph inside the session object. And then using session.run, we initialized first all the variables inside the graph. And then we execute the computation, fetching the result from the output node y. In TensorFlow 2, it's really straightforward because it's just pure Python. Therefore, we just create a function instead of creating a session, because TensorFlow 2 uses this new mindset that, in short, you have to use a function where in TensorFlow 1 you were using a session. So we just create a function, we just declare the two constant variables, the two constants, the B variable, and we define the same output operation, and we return the value. As you can see, we can execute as many times as we want the function. There is a short for loop there, where we execute the function every time, and we have to extract its value using the .numpy call, because even if we are using eager execution, this is not, of course, pure Python, but is an interaction between a TF tensor object. And therefore, every TF operation produces always a TF tensor. And to extract the computed value at runtime, we have to call the numpy method. OK, so we just defined and used the function using eager mode. And now we want to try to convert this function to its graph representation. So the test is to just add the decorator, TF function, on top of the function. And then I added the two print statements. The first one, as you can see, is the standard Python print, where we print the value of the variable y. And then it's followed by a TF print, where we print the same stuff, but of course bring tf.something operation. This is not executed during the runtime execution, but this is executing during the graph execution. So right now, when we're using tf function, we have two different environment of execution. One is that during the first call, we expect to see all the Python code executed, but no graph code executed. And then once the graph has been created, we expect to see only the graph code executed. So we can try to execute. We have declared the function, and we have also invoked the function. And this is what happens. So this is the first line. The first line is we are in the tracing phase. Therefore, as you can see, we have print, and this is a tensor with a value. Okay, eager execution is going on, and we are evaluating the value. But as you can see, this is print from Python. It's not tf print. Then we move on, and yes, we get this amazing exception. That's it. tf function, the corrected function, try to create variables on non-first call. Okay, so why? This code was working perfectly without the tf function decoration, but as soon as we decorated it, we get this exception on the first call. So to keep this short, this is the lesson. Because, of course, we have two different environment of execution. The first one is the Python environment of execution. So a tf variable object in eager mode is just a Python object. Therefore, when you declare the object, you execute the object, you call the function, and then once the function exited its execution, there is no more this object because it's been destroyed. Once it goes out of scope, the variable, there is no more the variable. But since TensorFlow, when using tf function, is trying to create a graph, and the graph in TensorFlow are static graphs, we cannot create dynamically and add variables to this graph every time we call this, every time we invoke the function. And in fact, the lesson is that a tf variable object in a tf function decorated function is the definition of a node in a persistent graph. So this is the solution. This is the way of reasoning when we are decorating a function and we want to use variables inside these functions. In short, we have to break the scope of the function because we have to be sure to declare the variables one and only one time during the creation. Therefore, this is the best approach. So using an object-oriented method, or an object-oriented approach, we can just define our class f. This is no more a function, although is callable. We define the private attribute b, this is our variable, and inside the call, we can just check if the variable has been initialized or not, and then declare it. So we are sure that only the first time this function is invoked, during the tracing, we enter in this condition and we declare the variable. Any other time we enter this function, the variable is already declared, and we are not trying to add a new node to a static graph. That is just impossible. So the second lesson to keep in mind is that eager functions that work correctly in eager execution are not graph convertible as it is. So in short, you have to keep in mind that while you are designing a function and you want to convert it to a graph in order to speed up its velocity, its speed of execution, you have to think about the graph that is being created. Now we can just have a look at what happens when we change the input of a function decorated with tm function. And this is a test that is needed because, of course, we are bridging two different words, because Python is a dynamically typed language. Therefore, I can define a function and just pass as input any type I want, and the function will just work. Instead, the TensorFlow, although everyone uses it as a Python library, in practice is a C++ library, and therefore C++ have a typing system, and it's really strictly statically typed. Therefore, you just can't pass, for instance, and I don't know, a variable with a different type with respect to the one that is expected in the method signature. Of course, you can cast, but this is not the case. So, to test what happens when we change the input, we just define this really complex function that is the identity. So we just define the function with the usual print and tf print. The one print without tf is the Python execution. The second one is a node in the graph, that is the graph execution. The third line is just the return, because of course it is the identity with some side effect. Of course, we just print the output. Of course, we have to keep in mind from the previous graph that the function parameters, the type of the parameters and the name of the function is used to create the key in the cache. And maybe this can be a problem. Okay, we can see now what happens when we pass tf_tensor as input. tf_tensor, of course, are native TensorFlow objects. And being native TensorFlow objects, I guess there shouldn't be a problem using it. In fact, in this test, we are just trying to create a float tensor A with the type of a float 32. We just print first call, we execute f using A as input. Then we redeclare another variable with a different value, 1.1, with the same dtype, and we do the second call. We do the same for the unsigned integer with the 8-bit, and we repeat the first call and the second call. Of course, here we expect to see, on the first call, to see the tracing phase. So we want to see the Python execution, and then the execution of the graph. But on the second call, we don't want to see the Python execution, but only the graph execution. And as we can see, this is what happens when we have tf_tensor as input. So on the first call, we have the Python execution, the tracing, the autograph, the creation of the graph, the caching. On the second call, we are just reusing the same graph. The same for a different type. So for instance, unsigned integers works fine. So since everything goes fine, we can just try to have a look at what happens under the hood when we decorate a function using tf_function. There is a module inside the TensorFlow package that is autograph that we can also use to inspect what happens when a Python function gets converted to its graph representation. As you can see, this is a machine-generated code, therefore is quite difficult to read. But as we can see, there is something that should sound strange, because this is a definition of a graph. And of course, for the one of you that are familiar with TensorFlow 1, there are a lot of TF control dependencies. That is the way to force the order of execution line by line, because in the graph, it's not that obvious that every operation should follow the same path, but in a graph, you can just execute more paths in parallel. So to condition the linear execution, like the eager execution, every statement is wrapped inside a control dependency of returns. But here, when we look at this generated code, we can see there is something strange, because the only graph operation here should be the tf.print, not the Python print. But as you can see here, we have two different statements. The first one, there is a print, and the other one, there is a print string. So we can look carefully and just formatting the code at the first line. The first line, as you can see, is just our Python execution print that is inside the graph code. But as you can see here, the second parameter of this AG, that means autograph converted call, is none. None is the second parameter of this function, that in this case is none, but is usually the owner of the operation. The owner of the operation in this case is nobody, because this means that TensorFlow doesn't know where this operation comes from. So it's not from a TensorFlow package. Instead, if we look at the previous one, we can see that on the second control on dependency, that the print statement is a string and the owner is the tf1 package. So in short, we can see, even if we convert to graph our code and we find some Python code inside it, and we just are unsure if the conversion is going correctly or if there is something weird going on, we can be sure that these statements are there only to force the order execution through the control dependency statement. But in practice, when the owner is none, every operation becomes a tf.noop. So it's just I do nothing, but it is useful to enforce the order of execution. So we can move on and see what happens when we use Python native type as input. So we just define a small helper function that is print.info that just prints the type and the value of the input. This is pure Python. And then we want to repeat the previous test we did on the TF tensor objects, but on the Python empty types. So we test first with the integers. We just declare an integer a, then we check if the type is correct. We call our function. Then we do the same, a second call with the value b, and we call again our function. We do the same with the float test, but this time we use the same value. For instance, there is a first call with the value of a that is 1, not integer, but float, and there is a second call with the value of 2 in floating point. So we can see what happens when we call with Python int as input. So we have the first call. We have the type info that is, okay, this is an integer. We have the Python execution, okay, and the graph execution. So we expect that on the second call to reuse the same graph. But instead what happens is that we have the same creation of another graph. As you can see, we have on the second call the Python execution with value 2 and the graph execution with value 2. So this means that using this way of decorating the functions, when we use Python native type as input, make to TensorFlow difficult to create a graph that is always the same and that can be reused. So the TensorFlow developers decided to just use the value. So what does this mean? It means that if you just create we invoke this function of 1,000 different values, we are creating 1,000 different graphs. And this is just bad. But things are getting worse. Things are really getting worse because we have the second test, and this is the call with a Python float. So as you can see, we have the first call. We have the Python execution and the graph execution. But the Python execution at the value of 1.0, so this is a float value. Instead, in the graph execution, we have the return of an integer. This is really strange. The same happens when we feed the float value of 2, but the return type is the graph execution of 2. And as you can see, there is no Python execution. So this is really weird, because this is just wrong, because if I'm giving to you a float number and you are the identity function, I want to have back a floor number, the same floor number. So exactly, this is me when I discovered this stuff. This is just make no sense at all. This is just a wrong behavior that I really don't like it. And the reason is because there is no auto-boxing of the types. So in short, tf function does not automatically convert a Python integer to a tf tensor. So in the same way, it does not convert a float to a tf tensor with the type of float. So the graph ID, when the input is not a tf tensor, is built using the variable value. And the reason is that we use the same graph for f called in one integer and f called in one float, because in Python, and this is the problem, one integer is equal to one float. As you can see from this really small test, having no auto-boxing and using in this way the corrected function causes a lot of troubles. Because as you can see in the first test, we have a for loop using a tf range call. The tf range call just creates a series of tf tensor values. And we are invoking the identity function g in this way. And as you can see, in less than half a second, we invoked this function. But instead, if we use a range, a Python range, therefore we are looping over 1,000 different Python integers, and we invoke this function, we are recreating a different graph for 1,000 times. So instead of less than half a second, we have to wait for more than 5 seconds. So the lesson is, if you are planning to decorate a function using tf function, just be careful and when you call it, wrap everything inside a tf tensor, because in this way you just define a graph once and reuse it everywhere. So we can just move to the last part of the talk, and it's where we analyze what happens when we use Python operators inside a function that is decorated with tf function. So this is a really dumb function that takes two input parameters, a and b, and we check if is a greater than b, we print a greater than b. If they are equal, we print that they are equal. If they are a is lesser than b, we print a is lesser than b. Or if all of that are false, that is just impossible, we print what? Guess what? This is the result. And this is just no sense. So what are the problems here? The problems are that the equal operator is not converted automatically to tf equal, even when we are using eager mode. But it checks for the Python equality between objects. This is a design choice of the TensorFlow team. For several reasons. The main one is that they are using tf tensor as key in maps, and then they want to just compare elements or do research inside maps. They want to use the Python equal operator. If they override the equal operator to generate a node, it will be a great mess. So Autograph converts correctly the if, elif, and else statements, but at the time of writing, it doesn't convert the Python built-in operators. So, as you can imagine, the first row becomes if false, if, elif, false, elif, false, else. So that's why it prints what? So the correct way of using tf function when we are creating a function that does comparison and it just use the Python operators, it's just don't use the Python operators. So there is the mat package, and you have to use the mat package because, of course, as you have understand, when there is Autograph that is parsing the abstract syntax tree of this function, it can just understand that if there is a tf mat greater, I know everything about this node, and there is nothing I have to do. So we have to simplify the life of the tf function decorator of tf Autograph. So this is the idiomatic way of writing functions when using tf function. But so the lesson is that please use the TensorFlow operators everywhere. Just don't fall back on the Python operators and all the Python types. Just do tf tensor and the TensorFlow operators. But fortunately, things are changing because as Rafael, that is another GD, wrote me, yes, in a release candidate, so before the stable version of TensorFlow 2, the comparison operators, so the greater and so on, are correctly converted, but the equal operator is still not converted. Therefore, the idiomatic way and the correct way of defining and writing code is to just use always the TensorFlow operators and never fall back and trust the autograph model so blindly. So this is a brief recap. When we are using tf function and we are defining this function, we have to take care of the tf variable objects. So we have to break the scope of the function and define it elsewhere. We have to think about the graph while we're designing this function, because of course we have to take care of the Python execution and the graph creation. You have to really keep in mind that there is no autoboxing. Therefore, we have to use TF tensors everywhere if we don't want to slow down our application by a lot. And of course, we have to write correct and idiomatic Python TensorFlow code. And so we have to use the TensorFlow operators explicitly everywhere. So the talk is finished, and this is a shameless self-promotion. This is the book I wrote about TensorFlow 2, where you can find, of course, stuff about tf.function, how to write Keras models, and there is a lot of computer vision inside because I do computer vision for a living. And that's it. Thank you.
So I think we can ask one question. Then my proposal would be that you can grab something to eat if you're hungry or to drink, and then we can continue at 8 if it's okay for you. So maybe one question, and then we can grab something to eat.